Now, naming cations. Ions have the same name as the metal atom followed by ion. So if it's Na+, it's the sodium ion, Zn+, zinc ion. If a metal can have different charges, then you have to include the Roman numeral. Fe+ would be iron 1, Fe2+, iron 2, Fe3+, iron 3, or you can use the Latin names. So we could use for iron 2, ferrous, for iron 3, ferric. You could use either one. Non-metal cations end in IUM, so NH4+ is ammonium, H3O+ is hydronium. Naming anions, you simply replace the ending with IDE. So H-, it's hydrogen, take the O-gen off and add IDE. Same with oxygen becomes oxide, nitrogen becomes nitride. Simple polyatomics end in IDE, hydroxide, cyanide, peroxide. Then we have polyatomics that contain oxygen, called oxyanions. When we name oxyanions, we use the common oxyanions, so carbonate, nitrate, phosphate. Those are the common ones. You want to memorize all of those, and then from that you can actually find 3 other polyatomics. If you add an oxygen, it becomes per. So in this example at the top, maybe this up here, I used chlorate as an example. Chlorate is ClO3-. If I add an oxygen, I don't do anything to the charge, I just add an oxygen, it becomes perchlorate. So instead of ClO3-, it's ClO4-. That becomes perchlorate. From the common, if I take one away, it becomes ite, so chlorite. Again, notice the charge doesn't change. And then if I take away another oxygen, it becomes hypochlorite. So this is how you would name your oxyanions. This is just some patterns in naming oxyanions. You can use it if you want. The biggest thing is to remember the same groups typically have similar patterns. So if you know perchlorate is ClO4, that means perbromate would be BrO4-. Now, nitrate, phosphate are a little bit different. Group 5 is where it gets kind of weird, but group 4 and group 6 work the same way. So try these practice questions, pause the video, answer them, and then come back and check answers. So one thing to change is it should say predict the formula for hypobromite and perbromate. But as you go through question 1, based on formula for sulfate, predict the formula for selenate, they're in the same group, which means they're going to work the same way. So instead of SO4, it will be SeO4, and then selenite, you take an oxygen atom away, so SeO3, 2-. Remember the charge stays the same. And then in the second question, bromate is analogous to chlorate, predict hypobromite and perbromate, which you see below. So hydro-anions are next. If hydrogen is added to the beginning of an anion, you simply put hydrogen in front. So if we have carbonate and we add a hydrogen, it becomes HCO3-. Notice the charge. We simply add these charges together. 2- plus 1 becomes 1-. In the next one, 3- plus 2 becomes 1-. -2 plus 1 becomes -1. So in this case, your charge changes because you're adding a +1 to it. So when we add 1 hydrogen, we simply put hydrogen out front, or if we add 2 hydrogens, we put dihydrogen. Sometimes instead of hydrogen carbonate, you see it written as bicarbonate. That's the same thing, and that's just instead of hydrogen, we can put bi. So instead of hydrogen sulfate, we could put bisulfate. So I want you to try to name these ionic compounds. When you name it, you simply put the cation name followed by the anion. So remember that your anion ends in IDE. And then in the last 3, I want you to write the formulas. So you have the first 3 you're naming, the last 3, you need to use the crisscross method to write the formula. So you can take a look at the names and the formulas for each of these. Notice that even though silver is a transition metal, it doesn't need a Roman numeral. Why doesn't silver need a Roman numeral? Well, silver is only +1. Silver doesn't have possible charges. Silver's only +1. Same with zinc. Zinc is only ever +2. So silver and zinc do not need Roman numerals. Look at the the summer assignment with the ions that you need to know, because that will help you as you work through that. Another thing as we go through, barium hydroxide, BaOH2. And then looking back up at the top, we have copper 2 perchlorate. Now some of you may have written cupric. That's fine. Cupric or copper 2, they both work. One is the stock system, one is the classical system. Either one will work. So the next aspect of nomenclature is naming acids. Naming acids is based upon the anion with the hydrogen. If the anion ends in IDE, you change IDE to IC and you add the prefix hydro. Don't forget to always include acid after. For example, if we have HCl, Cl is Cl minus, which is chloride. We change ide to ic, include the hydro out front, becomes hydrochloric acid. If your anion ends in ATE or ITE, you change ate to ick. Remember, you ate something icky. Ate goes to ick, ite goes to us. So if you remember I and us. So ate to ick, ite to us. Follow the name with acid. So if it's HClO4, ClO4 is perchlorate. Ate goes to ick, so perchloric acid. And here is more of a visual with naming the acids, looking at the anion, and transitioning to the acid name. And then finally, with looking at some nomenclature, we look at hydrates. Hydrates are a special type of compound. Hydrates are ionic compounds, which are salts, loosely bound to water. So CuSO4 dot 5H2O. So this dot is actually very important because that shows that it's one thing. So this would be named copper 2 sulfate pentahydrate because there are 5 waters attached to the copper 2 sulfate. So it's copper 2 sulfate pentahydrate. So we have to use the prefixes that we use in molecular compounds in front of the hydrate. And so speaking of molecular compounds, we can name binary or molecular compounds. When we list these, when we name them, we put the less electronegative atom first. So typically, we're going to name it just like the formula is going to give us. But we use prefixes to denote the number of atoms of each element in the compound. Mono is never used on the first element. So if we only have one element, we don't include mono. That would just be too repetitive. And then the ending on the more electronegative element, or the one that comes at the end, is changed to IDE. So CO2 is carbon dioxide. Notice it's not monocarbon dioxide, it's just carbon dioxide. CCl4, carbon tetrachloride. Okay, the prefixes tell us how many. We don't use the crisscross method, we don't use charges, we don't use anything except for the prefixes. So typically molecular compounds tend to be a little bit easier because everything that we need is given to us in the formula. If the prefix ends with an O or with an A, typically the 2 successive vowels just become 1. So N2O5 becomes dinitrogen pentoxide, not pentaoxide. We just use pentoxide. And then we have simple organic compounds. Organic chemistry is the study of carbon. Typically, it's carbon, hydrogen, oxygen, that's it. No metals are ever in organic compounds. Think of organic foods. Okay? Organic foods don't have metals in them. Organic foods are simply carbon, hydrogen, and oxygen. Organic chemistry, though, has its own system of nomenclature. We are only looking at simple hydrocarbons right now. We are not going to get into the overcomplicated organic chemistry until the very end of the school year. The simplest hydrocarbons are what are called alkanes. Alkanes mean single bonds. So notice each of these up here end in ane. That's because they're made of single bonds. The first part of the name just tells us how many carbons are in the compound. If there's 1 carbon, the prefix is meth. If there are 2, it's eth. If there are 3, it's prop, so on. So here is the list of prefixes. Many of them are similar to the molecular compounds. Some of them, though, are different. 1 through 4 is actually different. So we can have methane, ethane, propane, butane is 4 carbons, pentane is 5, hexane and so on. Again, this just tells us how many carbons we have in our compound. Now, again, these are very simple hydrocarbons. This is as far as we're going to get into the organic chemistry for now, but these are also types of molecular compounds. So if you see CH4, CH4 is not carbon tetrahydride. CH4 is methane. Just like if you see C2H6, that's ethane. That is not dicarbon hexahydride. That's ethane. So you do need to know the distinction between these. So that is the end of chapter 2. In chapter 2, we looked at atomic theory, how the atom came to be. We looked at all the different scientists and their contributions to the atom, as well as subatomic particles and how those make up an atom. We then moved on to isotopes and looked at calculating average atomic mass, and then looked at the mass spectrometer and its use in chemistry as well as other real-world applications. And then we got into the periodic table. We looked at the different groups and families on the periodic table, and then we looked at nomenclature. So that made up chapter 2. Please make sure that you read through the chapter, or at least skim through the chapter, just to make note of anything that we may have not covered in this lecture video. If you have any questions, do not hesitate to send me an email, ask me questions.